Oui, bonjour, bonsoir, Thierry Prédhomme pour le Cloud Native Meetup Romandie. On vous souhaite la bienvenue ce soir. J'espère que vous êtes confortablement installés ce soir. Donc, je vais commencer à vous présenter un petit peu comment ça va se passer. Et puis également, we will switch in English because we have our two speakers English speaking, which would be much better for them to be more comfortable since the beginning to follow up what will go. So I will share my screen and show what's gonna happen tonight. So up, here we go. So we will see first of all to how this is coordinating. So we are in a Zoom session, and you guys are following through the channel on YouTube. And this way, we will be able to follow the chat and all your questions. So please feel free to ask your questions at the time. Either I will be able to follow them and provide them during the speaker, or I will wait for the speaker to be finished and then to ask your questions. So please don't hesitate. Your question will be answered. Then you can join us on Slido. So this is an app as well to know a little bit where everybody is from, and this way we'll be able to see as well how many people and are connecting and where you're joining us, and to make this a little bit more interactive. So please join the Slido. And like this, we'll be able to see where you come from. We will start to see answers and joining. You have the QR code at the top left, and you just need to add the slido.com, the number, and like this we'll be able to see a little bit more people who are joining and where are you from. I see some names that we know already. So if you have your cell phone or your tablet next to you, you can easily join and via the QR code. So at the same time, I will present our speakers and do a little bit of the joining from St. Louis. So this is good. Thank you. And thank you very much. And thank you for joining. So I think this is good to make it in English for you. So tonight we will start with Longhorn with Jan Bruder from Rancher Labs, and then we'll have Ken's side. Sorry, Jan is joining us from Berlin as well. We'll have Ken's side from Chicago as well, the US, who's going to talk about the KUDO and who works for D2IQ, and then we'll make a short break of 5 minutes if anybody needs to drink a little bit or have a little break, and then we will finish last but not least with Argo CD with our own Raphael Pinson from Camp to Camp, and this way after we'll finish with a 15-minute Q&A. During the break as well, we'll have 5 minutes and we will ask you to participate as well with Slido. You just keep the QR code and to ask you what you guys want to see during the next meetup, what can be a topic of your choice, and like this we'll be able to share all this with all of you. So thank you. I see some location coming from nearby Geneva, Châtel Saint-Denis, and we'll see a little bit further Boston as well, which is very nice. So welcome, guys. Thank you very much for joining from a little bit everywhere. We can see a little bit later this map. And then, so that's what I was mentioning. So the agenda of the meetup tonight, making this 5-minute intro to welcome you in a good way. And then I will hand it over to Jan Bruder. So Jan, whenever you're ready, you can share your screen and take the lead.
Yeah, thanks Thierry. I hope you can hear me all right.
Perfectly.
Ok, wonderful. Merci beaucoup. Ravi d'être dans vos meetup. Okay, that's all for my French. Okay, so let me start by sharing my screen. That's always a good thing to do. Looks like screen sharing is disabled. I think you have to unlock it for me.
That's always what happens during demo. So I think all the audience is well aware of what happens. Now you're good.
Yeah, that's much better. Cool, awesome, thank you. Okay, so my name is Jan Bruder. I'm part of Rancher Labs. I'm a field engineer there, and I work out of Berlin, as Thierry mentioned, mainly in the German-speaking region here with our customers. And today I'm going to talk about an open source project called Longhorn, which provides a distributed storage for Kubernetes workloads. To start with, let's first get an idea about what we actually talk about. If we talk about stateful workloads, what does it actually mean? Because sometimes people mean different things by it.
Sorry, Jan.
Yeah.
I stopped your sharing by mistake. You can share your slides again?
Oh, okay. Yeah, I can do that. Just a second. Does that come up? Is my screen showing?
Yeah, perfectly.
Okay, cool. So back to stateful workloads. What are stateful workloads, or what do we define them as if we're talking about it in the Kubernetes way? Because some people just, some people think stateful workloads, or this is a database, nothing else. Other people think of stateful workloads, anything that keeps any state anywhere. So typically, when we start about deploying stateful workloads in Kubernetes, we're talking about applications that actually store their state in Kubernetes. So not a database client or some microservices that has a database client connects to a database outside of the Kubernetes cluster. So stateful workloads are really the application that write in the container file system, basically. We have a lot of stateless workloads, of course, running in Kubernetes. Sometimes they just have maybe some temporary storage. Maybe they're creating a configuration file on startup, or they're keeping some cache that does not really have to survive the container lifetime. And these are typically fine with just writing in an ephemeral storage, for example, an MTD, a volume that Kubernetes provides. Typically, yeah, I mean, most applications are not really stateless nowadays. I mean, the question is really where they're writing to. Do they write inside the cluster, in a file system? Do they write to a database outside of the cluster? So what is the state of stateful application management in Kubernetes today? We really see that the container orchestration is being adopted as a standard model for application delivery by many IT organizations. And it really becomes like a standard, like server VM-based deployments before. And that means, eventually users, they will want to operate all their application in a unified manner, and they don't want to differentiate between stateful and stateless application. They want to have a standard way to operate all the applications. If you look at the Kubernetes project today, stateful workloads really are a first-class citizen there. There's a special interest group called storage that is concerned with storage in general and volumes in particular. And if you look at the features of Kubernetes, you can see there's actually a lot of dedicated interfaces and abstractions that really have been created to facilitate the deployment of stateful applications. Most of them are probably familiar to you. We're talking about persistent volumes, claims, the container storage interface, things like stateful set, and so on. And there's always new stuff coming up, like, for example, volume snapshots. This is currently in the making. So Kubernetes itself provides all the blocks that you need to really manage persistent application, but it doesn't provide the storage itself. So you still need some underlying storage subsystem that provides the storage. And in the cloud, that's not a challenge. It's pretty easy, right? In the cloud, you can just you get basically storage as a service. You can just provision in block storage on EBS or something else. So it's not really a challenge, but outside of the cloud, it definitely is a challenge to get storage for the Kubernetes workloads and to decide to find the right storage as well. To get a chance to get everyone on board, because you cannot always assume that everyone is already familiar with the storage subsystem Kubernetes. Let's just have a quick 101 of that. So this is just a pod. A pod does not provide any guarantees or any functionalities for anything that you write in the file system to persist. What is the container file system? I mean, the container file system is eventually mounted to some basically temporary directory on the host file system. And as soon as the container is deleted or crashes, is restarted, everything that you write in the container file system is lost. A small improvement is the Kubernetes volume. So the Kubernetes volume really was mainly created for two reasons. The first reason was, the problem of containers crashing. So when a container crashes, the kubelet will try to restart it, but the data that you write in the file system will not survive. Basically, you will get a brand new overlay file system at the moment the container is recreated. The second reason the volumes were created was there was a need to share files between containers of a pod. The pod concept provides for some nice things like, configuration sidekick, or maybe having a sidekick container that processes logs of a legacy application that doesn't really follow 12-factor, and you need to output the logs somewhere and send it out. So this provides some really nice patterns, the volume sharing between containers. But there's still a problem with that, because the volume is bound to the life cycle of the pod. So when the pod is deleted or the pod is migrated to a different node, you lose the volume. So the other thing that's also with the volume is that you're able to consume different types of storages with it. So a volume could be mapped to an external NFS share, it could be mapped to a block storage device, and so on. This brings us also to another problem of the pod. So if you look at a typical manifest that has a pod which describes an inline volume here, you can see that in the pod, actually, you have to capture all the information about the external storage. So that's not really good, right? So first of all, a developer who maintains this manifest, he doesn't necessarily know that, and he probably also shouldn't know all these abstract details of the infrastructure. And the second problem is you're encoding basically infrastructure-specific information in your manifests, and that makes them not portable anymore. So to solve that, the persistent volumes were created. There's a couple of things about persistent volumes. First of all, they are their own resource in the Kubernetes API. So they have an independent lifecycle from the pod itself. Second of all, the persistent volume via the persistent volume claim, which is basically a request for storage, they abstract away the details of how the storage is actually provided. So this is this part here. And then there's two mechanisms to create a persistent volume via a request. One is basically a static approach in which an admin has to create or provision the underlying storage subsystem, for example, create an NFS export or create a new iSCSI LAN, and then create a persistent volume which has all the information that maps to that underlying storage. That's fine if you just have a couple of workloads in your cluster, but it doesn't really scale because at one point the admin wouldn't do anything other than create these things, and probably the application team would have to open a ticket for the admin to create these volumes. So that's not really nice. So to make this more dynamic, we have the storage class. And the storage class is mapped to a provisioner. It's It's basically kind of an interface that can be implemented by some controller, by some application part that not only provisions the storage in the storage subsystem, but also creates the persistent volumes in the Kubernetes metadata. So we go from here, where we have, in this case, the volume ID of an Elastic block in our own pod manifest, to a persistent volume claim, where you can see we have nothing that is really infrastructure specific. The only thing that we define here is what type of storage we want. In this case, single write storage or block storage, and how much storage we want. That's really nice. So, and today, what we're talking about today in this whole concept, really two things. We're talking about what is the component that takes care of fulfilling the persistent volume claims and creating persistent volumes in the Kubernetes metadata, and what is the component that provides the underlying storage subsystem. So if you run outside of the cloud, you typically run in a data center, which often has central storage solution. These central storage solutions were obviously not designed for Kubernetes workloads, and often really managed they have a lot of processes attached to it, and they're often managed by creating a ticket with the storage team, waiting until a LAN is provisioned, and so on. So it's not really cloud native. These central storage systems are also obviously typically very costly, and generally they lack portability, and often they don't have any integration in Kubernetes at all, if you look at a SAN and NAS solution. The second thing is, is basically day two operations for these volumes. Not only the provisioning, but you also want to manage backups and disaster recovery concepts and things like that for your application. And you want to do that in a Kubernetes native way, maybe via a CRD, via Kubernetes manifests to define like a backup schedule for your application. If you're consuming iSCSI LAN, there's really not such a thing. And even in the cloud, there are some limitations. Like, for example, Kubernetes, when you think about Kubernetes architecture, typically the best practice approach typically is to span across different availability zones. But that doesn't work with most of the cloud storage, because the block volumes from the cloud providers are typically only replicated within the same availability zone. And then finally, you could always create software-defined storage using some existing technology, like, for example, Ceph, which is a proven and battle-hardened technology, but it's also very complex. And if you want to operate just such a thing, you really need expertise to do that, especially if something goes wrong. And another use case actually for this is also edge compute, because increasingly we see people using Kubernetes for edge use cases. Like, for example, you're building a hardware appliance, a rack, and you're shipping it to a oil platform, right? So where do you get Kubernetes storage today? There's no SAN on the oil platform. So you want to have some more hyper-converged concept where you provide everything fully integrated. And that means running the storage solution in the cluster itself as well. So that brings us to Longhorn. Let me explain you what Longhorn is. It's a software that is concerned with providing distributed, replicated block storage in Kubernetes. It's also currently a CNCF sandbox project. Feature-wise, it provides volume thin provisioning. It provides the ability to do snapshots of volumes, typically used, if you have an application level problem and you want to revert, you can use that snapshot functionality. And you can also do backups, meaning that you can migrate these snapshots to an external system, like an NFS server or an S3 object store. So Longhorn also is topology aware. So if you label your nodes with, for example, different availability zones, like based on a rack or based on a data center failure domain, Longhorn can take that, understands that information and makes sure that replicas are always distributed across different zones or failure domains so that you can survive the failure of one of these zones. Finally, Longhorn also supports cross-cluster disaster recovery volume. You can also think about this as asynchronous replication. And this allows you to do constant replication of application data between two or more clusters. And I will explain a bit more in a second about that. Yeah, finally, Longhorn also, for Longhorn also comes with a GUI to manage, all the volumes and the storage, things like that. And of course, you can install as a Helm chart, which makes it really easy to install. So what were some of the core principles when Longhorn was created? First of all, volumes should be reliable. They should be crash consistent. They should protect against data loss, against failure of a node, right? So by default, volumes are created with 3 times replication. So even if you lose 1 or 2 nodes of your cluster, your volume, your data is still persisted. The second main goal was to have usability. We wanted to have a easy to use solution, something that even if you're not a storage expert or distributed storage expert, you would still install, use it, understand it, troubleshoot it. Skip ahead here. So let's have a quick view at the overall architecture of Longhorn. How is this actually built? So to integrate Longhorn with Kubernetes, obviously we use the standard interface, which is the CSI, Container Storage Interface, via a plugin. We then have a central component, which is the Longhorn manager. So this manager is in charge of orchestrating all the volumes across the cluster. This is the component that observes any requests for storage via the persistent volume claims and decides where to schedule these volumes. Then we have an engine, and actually we have an engine per volume. So this is really the microservice approach taken to the extreme. For every volume that we create, we have its own engine that is in charge of making sure that all the replicas are running and are in sync, and is also in charge if any replica fails to rebuild the replica and to move it to a different node. That's the engine. So if you go a little bit in detail on the engine, it all starts with a pod. The engine manages a replica, and it then exposes the replica on the node as an iSCSI, as a virtual iSCSI device, so that it can be mounted in the pod. Replicas typically are distributed across nodes to have a higher resiliency. And what happens if one of the nodes fails? The missing replica will be moved to a different node. It will resync from the existing replicas. We'll get its state here, and that's how it's restored. Looking at volume and snapshots very quickly. So Longhorn supports snapshotting. The snapshotting is very efficient, so it's like a delta. It's an incremental snapshotting that only stores the changes in between the snapshots. And this snapshot then allows us also to actually do a very efficient backup. So with the backup, we are also doing incremental backup style. That means we can do it quite often, up to every 1 minute. We can do actually backup. So that's why you can always call, you can call this also like an async replication. What are some of the special use cases? So I already talked about before about the ability to distribute across different availability zones, so that in case of a failure of one zone, you can actually migrate a stateful pod to a different zone, and it will still have its data there. Another thing is that for Longhorn, it's basically transparent what the underlying physical storage is. Storage is exposed to Longhorn as a file system. Okay, so that means Longhorn itself is not aware whether that's actually a physical local disk or maybe some disk coming over the network via fiber channel or iSCSI. And that also provides some nice things like, you know, you can easily extend existing volumes by attaching an additional local disk or by attaching an additional SAN and abstract it all via LVM volume group. And this is also a very nice use case. So this is a disaster recovery concept. So if you have a requirement to have your application running in different data centers or in different cloud regions, you can use Longhorn to do replication from one cluster to a second cluster. And this is a constant replication. It will use this. It will use basically a third-party storage as a way to transport the data in the second cluster, and the Longhorn instance in the secondary cluster will always fetch for the newest snapshots and will restore it locally, so it's always there in case that you have to do a switchover. Let's look at the current status of the project. So you can see it's Longhorn was G8 not a long time ago. We are currently at the 0.1.2 release. Joining the CNCF definitely helped with the growth of the community. We're now at almost 2K GitHub stars, and we have a worldwide node count of active Longhorn nodes of 12K. We have a fairly large community, so you're free to join us on the Longhorn channel on the CNCF Slack or on the Longhorn storage channel on the Rancher user Slack. What is the roadmap for Longhorn? So some of the concerns for the roadmap are, first of all, to improve node failure handling for persistent volumes. So this is not really a Longhorn specific problem. This is just a general, I would say, problem for Kubernetes, the way the node failure handling currently works. Because the way Kubernetes is designed is really, the pod guarantee is the most important thing. So what happens if a node goes down because of a network disruption? Kubernetes is not aware whether the pod is actually still running on the node. So in case of a single read-write volume, like a block storage device, Kubernetes will not allow the volume to detach on the Kubernetes level so that it can be attached to a different pod. And that means in the case of a node failure where you have like a stateful set or something running, you need to intervene manually. An admin operator needs to intervene, needs to manually delete delete the pod so that the volume becomes available for the new pod instance on the other node. Other things that we want to take care of is read-write-many support based on NFS, instrumenting Longhorn for Prometheus, so you can get nice statistics about your storage subsystem. And that also then allows us to do alerting and notification based on Prometheus. I talked before about the volume snapshotter feature in Kubernetes. We want to add support for that so that you can manage your snapshots and your backups via the Kubernetes native resources. And finally, ARM support is also on the roadmap. As you can imagine, Longhorn is quite interesting also for edge compute. Let me now quickly switch to demo mode. just get control of my mouse here. What's going on? Yes. All right. So I have, you can see I have a couple of clusters here. I've created one cluster here on DigitalOcean. Another one is running on vSphere. This one doesn't currently have anything installed, so it's just like a brand new cluster. So what I'm going to do, I'm going to just show you quickly how you can install Longhorn. It's pretty straightforward. As I said before, Longhorn is also available as a Helm chart, so you can easily do that via command line. But you know, I'm lazy. I like the GUI, and I like the way it allows me to configure everything. So let's just find the Longhorn chart and just deploy it right away. Let's see, maybe we can set some configuration about S3. Yeah. Just setting the secret that contains my credentials to access the S3 object store. And let's launch this off. So you will install Longhorn in the background. Shouldn't take more than a minute. In the meantime, let me deploy my AWS secret. In the Longhorn system namespace. Oh, sorry, I messed up. All right, that's created. And also, let's have a look at our first persistent volume claim that we're going to create just for testing. So when you install Longhorn, you will get a storage class assigned by default. This is called Longhorn. This storage class describes basically how the storage is created in Longhorn. So it describes things like replication factor and others. We can have a look actually. I think I have another no, I actually don't have one. Okay, so let's keep that for later. So now let's create the volume claim and then the pod. And let's do the same for the pod. Yeah, I didn't actually want to create it. I actually messed up. So let me do that. Let me just fix that. I didn't actually want to create it in the Longhorn namespace. Just fix this here and deploy again. It's fine, we can have running in the simple pod. So now let's see where our Longhorn is. Here we are with the Longhorn install. So Longhorn is installed. We can have a look at the GUI. And we can see there's already one volume. Is that maybe the volume I just created? So let's see. Yeah, that's it. So actually, let's just stay here for a minute and have a look. So this is the volume that was just provisioned in the Longhorn storage subsystem. What's nice here actually is you can actually see where the Longhorn is connected to, right? Because the persistent volume claim itself gets a UID, so it's very cryptic, not easy to understand. But Longhorn actually keeps track of where this volume is actually currently attached to. So you can see which pod this is running to. We can also get a little bit more information about this volume. So if you look here on the left side, we can obviously see the state of the volume and the current size. Longhorn provisions basically thin provisioned volumes. You can see I requested a size of 1 gig and currently not using much of it. We can also see, for example, state of backups and things like that, if it was ever backed or not. And here you can see it's actually nicely distributed across 3 nodes. So it gives me a lot of confidence in surviving crashes of cluster nodes and things like that. Under here you can see snapshots. So a snapshot is always stored locally. So snapshot is fine to protect maybe against any issues on the application level, right? If your application messes up and you want to go back to a previous state, you can use a snapshot to do that. The backup actually creates a snapshot and then ships it to the NFS or the S3 that you have configured. Talking about backup, let's just quickly configure a backup target. So let me just get my notes here because I'm always forgetting about the correct syntax. So I've basically configured here my the name of my bucket and the region in AWS. The secret is already configured, so that's fine. Just save that. You should now be able to see some backups. Yeah, you can see here's a previous backup that I created before. So that's working fine. Let's have a look at the nodes. Longhorn makes use of node labels to let you decide on which node you want to provide storage, because if you have a larger cluster, you might maybe dedicate some worker nodes just to provide storage. You can see by default we're not consuming all of the storage in the node. Right now, you have to also understand, if you look at the disks, that in this particular case, we're basically sharing the storage of the root file system, which you would not do in a production setup. So in a production setup, we would have a dedicated disk or at least a volume group just for Longhorn to consume. And you can also see it's currently, it doesn't use up all of the available storage. So you can see there's actually 67 available and only allows up to 48 for allocation. So let's go back to our pod, which I think we created in the Longhorn system namespace. Yeah, so let's do like something like this, kexec node pod, and data, there should be nothing there. Oh, what's going on here? Kexec. They have to container. Okay, it looks like almost like a WebSocket problem I have here. Okay, so let's not spend time on troubleshooting this and get to a real application. So what could be a good app to actually demonstrate persistence? Maybe a content management system. So I'm just gonna navigate to a different project here and launch a WordPress instance. And WordPress has basically two stateful components, the PHP server for asset storage and the database. Let's just enable persistence for both of them. So you can see here volume size that I want to request. Basically, I'm creating a PVC right in the background. So let's select the Longhorn storage class and do the same for the MariaDB. Okay. Let's deploy this. In the meantime, let's look at the other cluster they created. So you can see this is a cluster running on vSphere currently, and it already has Longhorn installed. but some different non-related volumes. And it also doesn't have currently run MySQL. And what I want to do is I want to set this up in a way that the data of the WordPress is constantly replicated to the second cluster. So that in case I want to migrate over or there's a disaster, I can easily switch to the other cluster running on vSphere. Theory, looking at the watch, I'm actually seeing we're running quite late. Do you still have a little bit of time?
Yeah, absolutely. You can finish if you have 5 minutes. That would be awesome.
Okay, so let me see if I can do it in 5 minutes here. Let's see what the WordPress app is doing. Okay, still starting up. But we can look at the Longhorn site, and we should have our WordPress here. And you can actually see we have one for MariaDB and one for Workloads. So what I'm going to do is now I'm going to activate or set up a schedule for backing up these volumes. I'm going to set this to once a minute. That's kind of the low or the smallest interval that you can do. And this retains the last 20 volumes, that's fine. So now I'm going to save this. And now we can see this has turned blue. That means that the backup is activated. And we're going to wait a minute or so, and it will show that it has taken a backup now. So WordPress is now running. Let's just quickly, change the state here. Oops, sorry. Oh. Okay, that's not nice. Oh. That's better. So now let me just quickly create a post to prove that we were here and did something. Let's publish it. Now it's published, and it should be here. Thing. You can see it took a backup a second ago, so let's just wait for the next one. But in the meantime, we can set up the async replication on the other side. So now I'm on the vSphere cluster, and we can now go to backups. And we should see the WordPress volumes. And now we're going to create a disaster recovery volume. So this will actually now set up the continuous replication to this cluster, to this Longhorn instance. We now stay at 3 replicas, not adding any tags or something like that. So now what happens every time a backup is taken here and stored on the S3, the Longhorn instance on the other side will be basically will pull that, and on any additional backup, it will fetch it from there and it will apply it locally so that it's available locally. So let's see. These are our 2 volumes. Currently, it does like the initial sync, right? Downloads all the initial data. Later on, it will be quite quicker because it's just an increment. It will just get the increment of basically the deltas of the backup. So as you can see, this one is ready, but it's marked as not ready for workload. That is because it's currently in the replication mode, right? So it's getting the changes the backup store. So to actually use this now, if I want to do a failover on this cluster, I have to stop the replication and I have to activate them. So I'll just do that together. You can see now it's stopped the replication. It goes into detached mode. And now I can simply, because right now the Kubernetes, like in Kubernetes metadata, I don't have any information about these volume threads, right? So now they just live in the Longhorn subsystem. So in order to use them now in the cluster, I can simply have Longhorn create the PVC and PV objects. Oh, okay. That's funny. Looks like I have to create the namespace first. Let me do this quickly, which makes sense. Let's see if that works. No, it doesn't prompt me for the namespace. That's weird. Okay. So now let's check our namespace. So one of the volumes is already restored. The other one is pending. So what we can do now, okay, so now they're ready. So what we can do now, we could just deploy the exact same application. And instead of creating a new persistent volume claim, we're just using the one that Longhorn created for us. So again, password, and probably don't need to set password, but anyway, you can see now for WordPress, I'm enabling this, but the difference is now I'm using the existing persistent volume. So let me just check about the name, of course, to get the right name here. So this is the one for the Apache, and let's do the same for this. This doesn't let me select it, so this basically is a stateless set. So it follows a certain naming scheme for the persistent volume claim, so it should automatically match the one that Longhorn created. And yeah, and then we can just launch it, and it should then reuse the existing volumes. Yeah, so at this time, let me finish up to give my colleague a chance to jump on. And in theory, we can do some questions at the end, maybe. Does it make sense?
Absolutely. Thank you very much, Jan. And I think for the moment, we don't have any questions so far. So
Okay.
from the chat. So for the people actually coming following via YouTube, please don't hesitate to post your questions online. So now we will talk about KUDO, Kubernetes Universal Declarative Operator, and we are joined by Ken Sipe from D2IQ. Ken, stage is yours.
All right, you can hear me fine?
Perfectly.
Good, perfect. Let me, I need someone to stop sharing so I can share.
Here we go.
All right. Perfect. Okay, I'll get started. I'm not sure what we'll have time for, but let's just get going. Let's see here. Play. There we go. Actually, it would be useful if you could tell me if this is viewable enough. Is that a good enough font?
Yes, it is.
Perfect. Great. All right. Excellent. So we're going to talk about KUDO. If you're not familiar, KUDO is newly added to the CNCF sandbox as well. My name is Ken Sipe. I'm one of the application developers. I'm one of the committers on KUDO and KUDO. Again, both of those being part of the CNCF. You can see me at Ken Sipe or Ken at day 2. I'm employee 22, so I don't I don't have the normal email. It's just Ken. I guess the value of being first. Let's see here. These are the contributors, and we have quite the ecosystem, and it's always great to give accolades where they're due. So this is the group of people that helped put KUDO together, and we're going to talk about what the value is regarding KUDO. So first of all, KUDO stands for the Kubernetes Universal Declarative Operator, and the focus is on operators. It was really great seeing Jan talk about stateful applications and what that means, what that represents. He's getting, it looks like the Longhorn is getting the tail end of what's happening there with storage. More on the front end, the orchestration piece is what we look at when we're looking at KUDO. There's a number of ways of building out operators, and we're going to talk about them. But one way, the way that we'd like to encourage a lot of people to use, if they can, is to do it declaratively. And we'll talk about some reasons why and how we do that. So I guess the problem description would look something like this. If you're going to create your own operator, first of all, who would do that? Who would create their own operator? Well, generally speaking, it's when you need additional orchestration within the cluster. Kubernetes alone, all by itself, does stateless applications extremely well. It has for years. Stateful came kind of later in its life cycle. It is pretty mature, but it requires a lot of handholding. It requires, you can see tooling coming out around it. Longhorn's a great example of that, where you want to separate out devs and ops, and you want to pull out of the manifest very specific things. But oftentimes, a stateful application requires more than that. And in fact, we can even go further than that with KUDO. We are starting to see people do orchestration where it's not even a stateful app necessarily, or maybe stateful apps are a component of it. But so who would be interested? Well, at a minimum, people, organizations, or projects that are doing stateful applications, maybe like MongoDB or Cassandra, a variety of things out there like that, right? What does it take to do that? Well, you have to actually understand Kubernetes. You have to understand distributed applications. You have to understand the APIs. You got to understand the security models and all the things that go with that. And that is just in Kubernetes. And then in all likelihood, the best tooling that we have available for building that out is in Go. Your application, the thing you're trying to orchestrate, may be written in a completely different language, C, Java, whatever it is. And you have to learn Go in order to build out an application that is an operator within that platform. And then you have to keep up with your application too. And then you also have to manage versions and manage versions in the Kubernetes way. That leads to tens of thousands of lines of code, which has been our experience. And what we're trying to do is let's ease that. The other problem that you have that we're trying to solve is the number of operators that are being created in the Kubernetes ecosystem is pretty high now. People are picking it up. It's becoming quite mature. And let's say you're just a regular organization and you've decided that you need to bring in, let's call it 20 different operators for whatever reason. Every one of those different operators has different CRDs. Every one of them has different ways of managing it. Every one of them has a different way of handling certain conditions and monitoring. And that we see that as a problem. It's a challenge. And so we want to unify that in some way. So you can also think of KUDO as, there was a project before, which is kind of getting dated. It's not getting as much love, but it was considered to be a meta controller. And in some ways we are similar to that. So what else is it? If you look at the mentality of the developers on KUDO, our focus is let's stay Kubernetes. We don't try to do anything outside of that. So we expect we expect users and operator developers to be familiar with Kubernetes, and we don't deviate from that. And it means knowing manifests, it means understanding and working within that ecosystem. So that's what we do. That's how we approach it. KUDO itself, what is it? Well, as a project, it has a number of different components. One is that it has a CLI. So we have a plugin for kubectl or kubectl, depends on how you pronounce that, but the CLI for Kubernetes, we have a plugin for that. And it manages a manager. There is a manager or controller that's run in the cluster somewhere, and it provides the management aspects. And the CLI communicates through that via the API, which is exactly what you would expect in a Kubernetes world. In another way, it's also a toolkit. It provides the ability to create an operator, some of the ability to create. It's like looking at Ruby on Rails where you're saying, like, I want to create another controller. We have that ability within KUDO as well. We're like, hey, I want to add a plan, or I want to add an ability to this operator. So those are the three components that kind of make up KUDO. We could go one step further, and we could also add that it's a test environment. So we also provide that ability. When you are looking to develop an operator today, and I'll talk a little bit more about that in a second, but if you're looking to create an operator today, you probably come down to three choices. And the choices are, and they're in an order that we hopefully make sense too, right? The first on the left is that you could create an operator framework through the operator SDK. So when you're doing that, first of all, you're writing Go code. You have a bunch of libraries at your disposal. And this is the lowest level of writing an operator, right? You are taking ownership of all the things. You're writing thousands of lines of Go code, and you have all the abilities that are available to you within Go and Client Go. Client Go being the libraries used to create operators or to interface with Kubernetes in general with Go. The second option there is KubeBuilder. KubeBuilder is like the Ruby on Rails. It is, hey, I need to create an operator. I'm going to say create a controller, and then it will stub out, create infrastructure for you. It'll create templates for you, and it'll basically have inline comments that say code here. You know, your code goes here. So like really old school development, the left-hand side operator SDK is like writing C Win API type stuff. KubeBuilder is like writing, C++, MFC or OWL type stuff, right? It is less code, but I still have lower level controls if I want them. On the right is KUDO, and KUDO is intended to be a way of writing code from a declarative standpoint. It comes with some limitations, but the focus is that it should hit a good percentage of people's use cases. And it's more like the Visual Basic of creation, right? It is just fairly simple stuff. The one thing I was gonna go a little bit further, and I won't spend too much time on it, is there's a growing desire by a large number of people to write in different languages other than Go. And I think it has to do with Kubernetes, infiltrating the enterprises, but there's some requests to write stuff in Java, and that's still fairly, for the most part, in the early stages. Anybody doing anything serious or real with operators today is writing them in Go or KUDO. Okay, so what does the architecture look like? The first is that you would have an operator, Kafka, Cassandra, are ones that we have within our space. The interface with the controller interfaces the Kubernetes API, and then the end works just as you would standardly see within the Kubernetes space. We have a built-in set of plans. So this is where orchestration comes into play. The value here is that I've been with Mesosphere, now day 2, for 6 years. In 2014, we were doing stuff like this already on the Mesos platform. Kubernetes didn't exist. It was announced in June of 2014. So we've been doing this for a long time, and we've been seeing roughly the same kinds of things, and they exist in the Kubernetes space. So this is what we did in the Mesos world, and this is what we've brought again with KUDO onto the Kubernetes world. And it might help to make sense of this. It might help to understand a particular use case. So the one I'm going to describe is one that I was one of the authors of in 2014 on the Mesos platform, and that is HDFS. So if you've ever provisioned HDFS, here's what it looks like. It's roughly, it's fairly simple, but you have some certain phases you go through. And if you look at Helm today and you look at what they do with HDFS, it's essentially a blast of a bunch of pods that should land, and you kind of hope and pray, and eventually maybe it will resolve itself to being functional, which is a weird way of doing it, but that's, and it requires humans, right? Like it requires humans. There's no way to reasonably expect that to solve itself without humans being involved, especially if you have repair issues or challenges or resource starvation issues and things of that nature. So what does HDFS look like if you were to provision it? The first is that you have a certain phase, and the phase is you need to land a bunch of journal nodes. And ideally, you would land 3 journal nodes across 3 different fault domains. The fault domains being either availability zones or racks or just nodes, right? Like at a minimum, you'd be across 3 nodes. So you need that. And once those land, then you would land a named node. And the named node would land, if you're high scale, you would want to land that on the same node as one of the journal nodes. And there's reasons, right? It doesn't have to be, but optimally it would be. So now you need to understand that when I land a journal node, that I need to have enough space to land a name node. And when I land the first name node, then I will format. And after I land the first name node and I format, I land a second name node and I bootstrap. So the operations that you perform are quite different depending on the stage you are in. After you have all the name nodes in place with all the journal nodes, then you can start loading up data nodes. And when you start scaling HDFS, it really is a matter of either vertically scaling name nodes, which get a lot of focus, maybe even some journal nodes, but generally it means horizontally scaling your data nodes. So that's the story. And what you have to be prepared for in the process of provisioning is at any point in time, you also could have a failure. You also may need to repair. So if a name node fails and it's the first name node, you still have to format. If a name node fails anytime after a format, then you just need to bootstrap off the other name node. So there's a series of logic or things, some you might call it expert experience, that an operator should be able to handle that you don't want humans to necessarily need to know. You don't need a wiki that you follow. You don't need the human touch. What you need is the understanding of that within an operator. That's the whole point of an operator. So we break down the KUDO architecture into having plans, phases, and steps. And any given phase could have parallel or concurrent, parallel or serial phases, and the same thing with steps. So a phase might be like the journal node phase. And you don't really want to go and start the name node phase until the journal node phase is completed. And completed could mean different things, but in all likelihood, it means that you've landed 3 journal nodes across 3 different fault domains and that they're all alive and ready. There could be things that you could run in parallel, and then you would know as the operator developer when that time is and what makes sense there. So this notion of how to intelligently manage the deployment and operation of an operator or any workload really on top of Kubernetes has a lot of value, and people are starting to see it, right? This whole idea of when is it ready? What's the status of it? What am I waiting for? Can be really hard. And for some reason, what we're trying to do here is trying to mature the orchestration space within Kubernetes. So, and what does that require? In the Kubernetes space, what is quite different than the Mesos space? In the Mesos space, you had multiple schedulers, and you had to create your own scheduler. In the Kubernetes space, we have one scheduler generally, even though you could replace it. But generally speaking, you think of one scheduler. You have multiple controllers that orchestrate it. So this is the creation of controllers that manage orchestration across the Kubernetes space. So if you want to get involved, we have a KEP process, and to a certain extent, it's really the KUDO enhancement process. It's the KEP process that we have in Kubernetes that's been kind of slimmed down. We don't have SIGs. We don't. There's a bunch of requirements that the standard Kate's enhancement process would have that we just don't need, and it's overhead. So we have a simplified process. You'll see all of the KEPs out within our repository if you're looking to get involved and understand that. We have a monthly now Zoom session for looking at KUDO and KUDO and adding in feedback and getting responses. We'd love to hear from you and help solve your problems. That's part of what we do. So, you know, it might be easiest actually to just jump out here and show off a few things. So what I have running now is Kind. So I'm just running locally. I can run this anywhere. I spend my day using this out on Amazon or AWS, I'm sorry, they're the same, or Azure, or GCP, or whatever. So there's a number of places that we would operate. Of course, locally makes sense as well. Again, if I wanted to so I have a naked Kind cluster. I didn't do anything yet to it other than just install it or create a cluster. Here I'm going to spin up a KUDO instance, and this is going to load up a manager into that cluster. It's actually going to do a number of things, right? It's going to set up my SA. It's going to set up meaning my service accounts. It's going to set up my CRDs. There's 3 of them for KUDO itself. We do require now, because we do work with a webhook for managing changes to the CRD. We do have a webhook in place, and we have to have a CA manager installed. Well, in Kind, I'm not going to have that. So when I have this extra flag here of unsafe self-signed, it's not something you would run in production, but we want the ease of being able to manage this in a development environment. You see the -W, what it's saying is let's wait until it's done installing. There is a bug on this version, and the bug actually is these messages you see that has been ripped out. I reported that bug a week or 2 ago, and it's been modified on masters. So that really shouldn't be there, but it does tell you what's going on here. It's saying, hey, the manager's been installed, but it's not healthy yet. It's not ready, but now it is. So now we have something running. We could actually, you know, say KUDO version. We get the version of the KUDO that I'm actually working on. I could say KUDO get instances, and there are none because we didn't install none. We didn't do anything yet. But let's say I've got an example here. First of all, let's do this. We have a repository, a community repository, and you can point that to anything. So you could point it to your own repository. And I could say I need to search for maybe Flink, and it'll say, well, these versions of Flink are out there. Or I could search for Cassandra, and it's like, well, there's the version of the current version of Cassandra. Now it's the latest version. I can actually get all the versions that are currently available, that kind of thing. So I'm actually communicating to, this is hosted on our S3. It's what our community is, but again, I could look at my my repositories, and there's a list of the repositories. I have some private ones, I have some test ones, I have a variety of things that are out there, and I can configure this any way I want. So you can just be completely, we have users that are air gapped and have only connections to their internal intranet, and that's totally possible. It's a completely reasonable thing to expect. So now that I have something there, maybe we want to install something. There's a number of ways that I can install. One is I can install straight from, you know, I could say KUDO install of Zookeeper. I'm going to shortchange some of this. I'm going to actually do an install of from a file. So I can go to the repository, but I can also do it locally. So I'm pulling the files from my local file system and saying, hey, I want to install the demo for Flink. Now, what's interesting about this is in order for Flink to run our Flink demo, it actually will have to install Zookeeper, and it'll have to install Zookeeper because it needs Kafka. It will need Kafka to operate with the Flink. And then we have the Flink demo, which is actually generating data and such. So just by installing this, we're actually creating a series of CRDs that are deployed to the environment. And then based on that, we are spinning up instances of things. There is a plan executed. So it's easiest to see that plan if I just say, hey, I want the current plan status for the instance of Zookeeper that was installed. And so now we see that breakdown of the plan along with the phases and the steps and where we are. So you can see that this is in progress. I know exactly where it's at. I could say, hey, give me the status of the Flink demo itself. And so here it's in progress, but it's waiting on dependencies. So we have dependencies currently on Zookeeper and Kafka. If I switch back to the Zookeeper one, I could say that I want to wait. And so now I'm just sitting here and you can't see it. You can see the time refreshing, but I'm sitting here waiting until this is actually done. And I will get a phase of complete once we have validated that the step that we're in for Zookeeper is finished. And then at this point, it's just all Kubernetes stuff. I can get in here and say, well, give me pods, and I'll get a list of pods. So there's Zookeepers that are spinning up. I could say, go in here and say, well, KUDO get instances, and they'll say, well, here's the list of instances that we have. So I'm just interacting with Kubernetes really through a CRD. And now one of the challenges that I mentioned earlier is we have a bunch of different operators and they have all different interfaces. And we've just simplified that, right? The Kafka and the Cassandra that we have as operators, they both have plans for backup. If I want a backup, I just invoke a backup plan once I'm ready and available for doing that. So I've simplified a number of things that, we're a little bit ahead of the curve here because organizations, unless they're really, really advanced, aren't running into this problem yet, but they will, right? It's just, it's expected. So we'll need a way of solving it. And there's a couple of ways of solving it, right? One is creating a default standard. The other is having a bunch of people gather together and try to create a convention and probably try to standardize on CRDs. You're also seeing that today, right? Today, we actually see the community around Cassandra trying to consolidate their CRDs. And that should be expected, but it goes beyond that. How do you go from Cassandra to Kafka to Mongo to Neo4j? How do you get all of those in a reasonably good user experience? Or are we just going to have a hodgepodge of things? So that's the question that we need to hopefully solve over time. There's one other thing that'd be worth pointing out. I would recommend that maybe invite me back, if you will, for talking next, whenever it makes sense. But one of the things that came out of KUDO is the creation of this test harness, which was KEP8. We actually broke it out into its own separate project, which is called Cuddle. And when we cuddle things, cuddling is essentially a way of testing, and it tests things in declarative ways. So when you look at how do we test things in the Kubernetes proper, what you would see is a bunch of shell scripts. It's really, really challenging. It's a bunch of SH shell scripts where you're asserting things. Now, I'm super happy anybody's testing, so I'm not gonna bash that at all. We should be grateful people are testing. And what we're talking about here is end-to-end testing, right? When we're end-to-end testing, it's just easier and better to actually look at YAML, right? It's actually better to look at it declaratively. So why don't I code this up real quick and see if I can find an example, and then we'll call it a day. Let's see here. Tests, here we go, Zookeeper tests. So we have a series of tests. I'm not sure, my thing seems locked up. What are we doing? Cancel that. Tests. Okay, so step 1 or step 0 is our install. This literally will install Zookeeper for us. It'll go through the steps of installing. After we've installed, we have our step 0 assert. So now here's a series of manifest files that are partial. They're partial YAMLs, they're not complete. And it will assert that the values that are assigned here are true. So in this case, probably one of the more important ones is that, this stateful set will have a status of ready replicates of 1. And it'll sit there waiting until a timeout until that is true. Otherwise, it will then fail. So again, I could go into a whole lot on this, but I would think one of the more meaningful and powerful things coming out of KUDO is a thing called KUDO. And the reason why I think that is because KUDO, it's gonna help people with operators for sure, which is great, but KUDO is useful for everybody. It's useful for anybody doing anything within the Kubernetes space. All right. I think we're closing in. We do have a CLI, as mentioned. We do have the ability to have planned upgrades and updates, and then a plan that you walk through when you're doing an upgrade so you can confirm things. As I mentioned, the package command allows you to create an operator from scratch if you wanted to. Normally I would go through a demo of that, but I think we won't have time. If I want to, you've seen me do the install. There's some things here that we're looking forward to doing, like adding in metrics and alerts and some additional hooks. We already have a hook for cleanup hook. So when you delete something, a cleanup plan will be invoked. But we just ran across a challenge where sometimes cleanup is more of a post cleanup than a pre-cleanup. And I know that might be a little bit low level detail, but being able to work out those details is super valuable and important to us. We already have the ability to do dependencies as you've seen. I gave the example of that. We're already in the sandbox, so I'm using some older slides. It was called in kind of last minute, so this is already kind of true. We're already in the sandbox today. With that, thanks very much. Get involved. We have a KEP process. We have a community meeting that meets monthly. We have, of course, the repository. We have our website out there with the docs that are pretty good, I think. And we're always available on Slack. So if you go to slack.io, then go to the KUDO channel. And frankly, unless I'm on vacation, I'm probably always there. I'm always reachable. And frankly, if you left a message pinging me directly, I will at least get an email and be able to respond to it at some point in time. So with that, that's what I had. I'm open to thoughts and questions if people have them. And I will stop there.
Thank you so much, Ken. So far, I think Raphael has a question for you.
Yeah, I have a question.
Please.
So you were comparing KUDO in the beginning with Red Hat's Operator SDK and KubeBuilder. So I've used KubeBuilder typically to write a plugin for Cert Manager. Is it possible to make these plugins using KUDO, or is it a different scope?
Yeah, that's a great question. Well, I was going kind of quick, and I might have left a few things out too. Operator SDK, I'm actually one of the co-chairs on the community meeting for Operator SDK, and the Operator SDK and KubeBuilder are actually merging. So there's enough synergies that we're merging those projects, but the interest groups are still separate. And then to answer your question specifically, I'm not sure. I would have to know a little bit more about what the plugins are doing. There's no question to me that there are times when you would want to do something outside of KUDO. So examples, when you want to know, the intimate details of how the underlying tech, let's call it Cassandra, right? If you want to know what the underlying tech is doing and you need to be able to convey that up, KUDO today doesn't have any ability to do that. We were talking about a year ago being able to have plugin code that would do those things for you, so that you would basically have to write a small amount of code and still mostly be declarative. We're not at that stage yet, but I totally see the point. So examples, just to be very clear, you might have lost a slice of Cassandra and it's deemed as not retrievable. You're not able to recover. So you might create another instance, and you might need to rebalance. The act of rebalancing brings it's meaningful, right? The fact that you are rebalancing, potentially, it's likely that you do not want to do a backup when you're rebalancing, or you wouldn't want to restore when you're rebalancing. There's a number of things, and frankly, at the highest levels of scale, you may be able to serve, but you may be able to serve only at a lesser service level agreement than your optimum service level agreement. So those details, as an operator, I totally see the need and value of doing that. KUDO today doesn't have that ability, but we're we're definitely mindful.
Thanks.
Yep.
So far I'm following the chat on YouTube. Let's not forget that there is a 25-second delay between the questions. So there is no questions for the moment. But thank you so much, Ken, and thank you so much, Jan. So after I would do a couple minutes of break. And so you can as well join Slido for the second question. We are always keen on knowing what people want to hear about in the meetups, for you, for us, to know whatever the audience is interested in. So please join Slido with the QR code that you have here, and like this we can add some topics and see where everybody is motivated for. We will get back just after couple minutes, 5-minute break, and enjoy to rest 2 seconds, and then we have last and not least Argo CD and the question if you have. Thank you very much, and see you in 5 minutes. Nous revoici de retour. Thank you very much for coming back after this 5-minute break. So where are we at the moment in terms of which cloud native topics you would like to see in the future? So we can see 2 people already wrote Terraform, monitoring tools, Traffic. I'm not sure if I pronounced that right. I'm the only non-technical guy here in the room, in the virtual room. JSON preprocessors and Surf Manager. So don't hesitate to add this, because Slido.com and with the number 32712 to make sure that you can add during the next talk. As well, I wanted to share with you a great news for Switzerland. So we are part of the Swiss Cloud Native Alliance with our colleagues from Vision, from Zurich, and from Puzzle from Bern. So the 3 entities created the Swiss Cloud Native Alliance in order to make sure that we bring the best to all the people interested in cloud native technologies around Switzerland, usually in English or in German. So thank you very much. So don't hesitate. There is I will be able to share the slides afterward. I will ask to Jan and to Ken to share our slides if possible. And like this, for the people interested, please give us your email address on the Meetup site, and we will be able to share those slides with you. Then my my slides are not in order. So now we will join with Argo CD with Raphael.
Thank you, Thierry. So let's get started with this. Oh, there we go. All right. Let's get started with Argo CD. We're a bit late on the schedule, so I'll try not to take too long with my demo. So my name is Raphael Pinson. I've been working at ChemScam for the last 8 years. Usually define my job as infrastructure developer, and I've been mainly working in the fields of Puppet, Terraform, Kubernetes more recently. You can find me obviously on all this stuff here, usually as Refing. So at ChemScam, we use a lot of technology to automate things, from configuration management with Puppet to observability, content orchestration with Kubernetes, provisioning, and so on. And we're always looking for ways to automate things. And these days, in the last few years, obviously, you know that everything, or pretty much everything, has been about containers. There's containers everywhere, whether you're still using them locally, using Docker Compose, or using Docker Swarm, or already using Kubernetes. Lots of things are about containers. So when it comes to deploying these containers, this is a good practice that comes from the DevOps movement, which is continuous integration and continuous deployment. So we try to use CI. So typically, in the last few years, we've been using GitLab CI for this. And with this CI engine, we want to build the images, the Docker images, tests, and then deploy using Kubernetes. lots of tools have gotten together in the last few years for this. So here, these are some of the tools that we've been using for years, and eventually they're just converging and getting integrated into this Kubernetes environment in one way or another, in such a way that everything becomes automated and allows for automated deployment, for example. And that's not even just touching, it's just touching the top of it, because if you dig a little bit deeper, there's actually tons of tools now, just in the CNCF landscape. Just look at the CNCF landscape page to have an idea of just how many tools are being added. And we've seen examples with the last two talks. So when it comes to deployment, what is the problem actually? Everything in Kubernetes is deployed using manifests, using YAML or JSON files. Actually, internally is JSON, but usually we use YAML because it's just easier to write. And the problem is, if you deploy all these manifests manually, then you get a lot of different definitions that are not tied together, even though they should belong together. And you've got also the problem of how do you inject variables? How do you templatize this files, this manifest, to inject variables on the fly, so you can use templates and just change a few values when you instantiate them. So the first answer to this obviously is Helm. A lot of people are using Helm. We've seen Helm being used in the previous talks. And Helm is a tool that was made to be a package manager for Kubernetes. And so Helm provides metadata in the form of a file called chart.yaml. And this chart.yaml contains the name of the chart, the version of the chart, the version of the application that is being deployed, optional dependencies as well with other charts. And then a Helm chart also provides templated manifests using Go templating. So you can have your YAML that is templated, and then inside this templates, there's some Go template code that can be used to inject values. And it also provides default values. So a chart can come with default values, which can be overridden when you instantiate a chart. So this provides the basic idea of a package. So you can have a Helm chart for WordPress, for example. You can have a Helm chart for any application you can think of, pretty much, and it will instantiate all the deployments, which in turn will instantiate the replic assets in the pods. It can instantiate the PVCs for volumes. It can instantiate the ingresses, for example, for routing and all that things, which are necessary to run an application in production in Kubernetes. So Helm also provides the Helm Hub, which is a central place where you can register your own Helm repository. So you can make your own Helm repository using either static index.yaml files served on an Apache or other web server. So typically we build this using scripts that will build the index.yaml and then deploy it behind a web server. Or you can use more advanced systems to deploy, to provide a Helm repository using Chart Museum, for example. And then on Helm Hub, you can register your own repository. So you've got a lot of searchable lists. You've got a list of searchable charts that are available on different repositories, and it tells you where you can find which application. So that you can easily install them. So based on this, when you found the chart that you're interested in, you can just add this repository locally and just call Helm to install this chart in your Kubernetes cluster. So that's fine. That's fine, but it's not really perfect. There is a term that has emerged recently, which is GitOps. GitOps is not really a new way of doing things. In a way, we've been doing it for a very long time. The idea is we want to store and manage the entire source of truth for a project in Git. Let's say in VCS, but Git is the VCS of choice these days. And so with Helm, you already have a good start, because the charts are available with metadata. So you've got some kind of declarative way of deploying an application. The problem is the instantiation of the chart itself is not declarative. You need to call Helm in order to start to instantiate your chart and pass some values. So typically the value files could be stored in Git, but you still need a way to put the Helm charts together and manage the versions. One thing you could do, for example, is a top chart that would inherit, that would depend on other charts with specific versions and specific values. But another way of doing this is using a tool that is called Helm file. So Helm file allows you to use a single YAML file, and this YAML file will list the Helm charts that need to be included with their versions, with the value files, and with optional overrides as well, because you might want to have a static value file to inject into your application and optional values that are taken dynamically, for example, to inject secrets when you instantiate your application. So that's fine. You can already do something that is pretty good this way. You can commit the YAML, the Helm file, the YAML to a repository, and then maybe using CI/CD. So whichever tool you want to use for CI/CD, you could automate some kind of continuous deployment into your Kubernetes cluster using Helm file. Lately, though, Helm hasn't been exactly the preferred way of deploying things. It's still used a lot, mainly because there's a lot of Helm charts that exist. They're already there. There's already the metadata, the dependencies, the templated YAML is already there. But a tool that has emerged as a replacement for the deployment itself is Argo CD. And Argo CD typically takes care of all the automatic deployment based on the source of truth that is kept in Git. So originally we went with just Helm, and then Helm file, and Argo CD takes the next step in the deployment. So what does it look like? Actually, Argo CD has a web interface, which can be useful for debugging what's happening, because all the things create a lot of objects. And so in Argo CD, you'll see for each application, and the application is a concept that comes from Argo CD. It's a custom resource definition that comes with Argo CD, and each application is instantiated with Kubernetes objects attached to it. And so usually in Argo CD, what we do is that there's a top application that is called the app of apps. And the app of apps is the application that manages all the other applications managed by Argo CD. And then in each application, you can start one or several charts that will be tied together with values. So this is an example here of a namespace in our cluster that was made for Puppet. So IS for infrastructure services, Puppet. And then in this application that manages the namespace, we've deployed several applications to manage the different components that we deploy in that namespace. And each of them is an Argo application. So if I click on one of them, I will get to the part that manages this application. For example, if I click on the Puppet server one, this is what it looks like. And you can see that this IS Puppet server application manages lots of different Kubernetes objects, and you can see how these objects are chained together. So where it gets us to eventually is that in order to deploy your applications, all you need pretty much is a Kubernetes cluster and Argo CD. And once you have Argo CD plugged into your Kubernetes cluster, you can deploy everything else, because everything else is in fact deployable as YAML manifest for Kubernetes objects. So that raises a question of chicken and egg. Well, actually not exactly chicken, because it's Argo CD. So let's say octopus and egg, right? Which came first, the octopus or the egg? So you want to manage Argo CD as well. Argo CD is an application that is deployed on Kubernetes. So how do you manage Argo CD? So the idea is, let's start Argo CD first and then have Argo CD manage itself eventually. So I want to show you a little demo that we've put together in the last 2 weeks, if I'm not wrong, with the idea of making it more generic so we can deploy this standard on every Kubernetes cluster that we manage. So currently this demo is based on a Makefile, some script, and there's an Argo CD directory in here. So this is a Git repository. And in this Argo CD directory, we have the definitions for different applications. So the steps we have here in the Makefile, I'll just switch to this. There's several steps in here, and we're using Terraform to set up a cluster. Because this is a demo, we're using K3s, so the rancher people here will be happy. And so the first step is the provisioning, which will create a kubeconfig.yaml, which we can use as a result. And this this runs in Docker, so we're using Docker containers locally, so we don't need to install Terraform or Argo CD or other tools. So the first step here runs Terraform with a provision script, and I'll just show you what this provision script does. It's simply a script to wrap around Terraform, so it installs, it goes into the Terraform directory and then runs Terraform init, switches to the workspace with the name of the cluster, which is the name of the branch we're on. And the idea of doing this is that we can use the same Git repository with different branches to do a blue-green approach to compare clusters and test switching between different clusters or differences between cluster versions. Then we do an init again, because if it was already instantiated, there might be a need to upgrade the modules. And then we do an apply and a plan. So if you're not familiar with Terraform, Terraform is a tool to automate provisioning using connections to the cloud interfaces. So in this case, it will automate the creation of the K3s cluster. I can just show you quickly what it looks like. This is pretty simple. Here it is. We're just creating a Docker volume for the K3s server, a Docker network to let the K3s server and the K3s agent communicate with each other, and then the Docker image for K3s, the Docker container for the K3s server, and we're just launching the K3s server and the K3s agent on the same network so that they can talk to each other. So when I run this provisioning, the result is that I get 2 Docker containers. You can tell I've deployed it 2 hours ago. So I've got the K3s server and K3s agent. And the point of using this versus using K3D, for example, is that this is a fully idempotent approach. So I can run make provision as many times as I want, and it will just converge towards my target state, which is having this cluster deployed. The second step here, and this is where I want to get really, is once the cluster is deployed, we want to deploy Argo CD. And so this is the second step here. It's the deploy step. And I can show you again the script for the deployment. And the idea is that this step would be extremely standard. So in our case here, we've deployed a K3s cluster locally, but it would work exactly the same if we deployed an EKS cluster on Amazon or an AKS cluster on Azure, etc. So the idea here is we want to check if Argo CD is already running to make it idempotent. If Argo CD is not running, then we deploy Argo CD here. This is what it does. We want to avoid using Helm to keep the state of the deployment. So we're using Helm template, which is what Argo CD does. So Helm template will render the template to set up Argo CD, and then we pipe it into kube control or kubectl, as Ken prefers to call it, so that it creates the Argo CD deployment in the Argo CD namespace. Then we wait 30 seconds, so that the pods are declared. We're sure that everything's fine, even if our laptop is a bit slow. And then we wait for the pods to be ready. Once this is done, we know that Argo CD is set up. So if it was already set up, we skip this part. Otherwise, we set it up, and we know that once we're here, Argo CD is ready to work. So the next step is creating the app of apps. So there's a bit of logic here to create the tokens and so on. I won't get into the details, but the idea is that we generate the app of apps, and then once this is done, everything else can be deployed using Argo CD automatically. So then we get into the Argo CD directory, and that's where we can define all the resources we want to deploy in our Kubernetes cluster. So here we will find the Argo CD chart itself, the Argo CD definition. So you see that there's a chart.yaml, which we usually use this in Argo CD. We define a local chart. And the point of doing this, it's non-mandatory, right? But the point of defining a local chart is that if you want to add new resources to the existing chart, it will they will be deployed together within this chart. Whereas if you just point to an external chart without declaring a local chart, then you won't be able to associate the resources. And here in this case, we have a local definitions. We have two local definitions, in fact. We have a certificate for Argo CD, which is defined here, which is a cert manager. Cert manager is one of the first things we deploy with Argo CD in the cluster. And then we have an ingress route, which allows to access Argo CD from the outside. So these two are not defined in the standard chart. So by defining this local chart and these two resources, we're able to manage them together in Argo CD. And then we find the same thing here for the app of apps. The app of apps is rather simple. It only contains an application object for every application we want to manage in Kubernetes using Argo CD. So there's the app of apps itself. It manages Argo CD as an application. It manages the app of apps as an application as well. And then every application that we want to deploy in there, for example, Cert Manager. This is how Argo CD knows where to point for the definition. So here we're saying, here's a new application called Cert Manager. And this application you'll find in the current repository. This is the repository we're using at the moment in the Argo CD /Cert Manager directory. So here we're in the Argo CD directory and in Cert Manager. So this is how it gets put together. So with all this, when we run make provision, it deploys the Kubernetes cluster. And the idea is that it would be pluggable to deploy on different clusters. And then when we run the deploy, it deploys Argo CD, and then everything is automated after this based on Argo CD. So I can show you the, where is this? Here. The demo itself, the code I'm using to run this is public. So you can look it up here, camp/k8s demo. And because it's using containers, pretty much the only dependencies you need are Docker and GNU Make, and that's pretty much it. So everything runs in containers. And the idea is that we can also plug it into a CI, for example, GitLab CI, instead of using local containers. So when I run this, there will be several things available. I just started a port forward to show you traffic. So traffic is launched inside the K3s cluster, and the services are deployed here. So we have services for Prometheus, for Grafana, for Alert Manager, for Argo CD itself, that are deployed and available automatically. Let me see if I can find the link for Argo CD. It should be here. Yeah, Argo CD.apps.base domain. So normally if I copy this, yeah, obviously the certificate is self-signed because this is launched locally, so I can't use Let's Encrypt. So I just need to, that's admin. There you go. So this is what Argo CD looks like here. We've got the app of apps here, which manages all the other applications. And then if we click on a specific application, like you see, it manages itself even, like Argo CD, for example, we see the definition of the Argo CD application, and it manages all these resources. And again, we see that the ingress route that we added here, as well as the certificate, which is probably somewhere there, I don't see it, are added within the same application. They're tied together because we use this local Helm chart approach. We can also see the other applications that were deployed with an ingress route. So here we've got Grafana that was deployed automatically with some default dashboards. So there's the dashboard for Argo CD itself, which is a standard dashboard, which tells you how long it's been up, the number of applications that have been deployed, the status of reconciliation of the applications, because Argo CD will actively, contrary to Helm, it actively tries to reconcile the state of the resources it manages with the Kubernetes cluster. And we can also see there's some standard cluster monitoring dashboards here. This is what you find when you deploy OpenShift, for example, or Rancher has an equivalent also based on the same project. And we've got some for Cert Manager as well. So all the things is deployed by default just by running the make file. Sometimes Helm doesn't take care of everything you want. You can add new resources like I showed using a local chart, but sometimes you want to modify existing resources and the variables are just not available for this chart. So there's another tool you can use, which is called Customize. And Customize can be a different approach to deploying, or it can be actually complementary to a chart. So what we've done here, and I can show you hopefully, if I'm not, go CD here. I think it's in here if I'm not wrong. Yeah, is that you can add a new plugin to manage the way that applications are deployed. So there's basic plugins that will use either Helm or Customize, depending on the files that it finds in the project. So here we've added a new plugin called Customize Helm, and this Customize Helm plugin will actually use Helm for the templating, and then it will use Customize as a second step. And the point of doing this is that you can have both a Helm chart to inject the values, build a base application, and then optionally use Customize to modify values that were not exposed in the Helm chart. So this had allowed us to have more flexibility on applications that didn't have the values exposed for what we needed. Finally, I'd like to just give a heads up on another project that integrates Argo CD in an interesting way. It's Project Sin by our friends Vision and Zurich that are part of the Swiss Cloud Native Alliance as well. And Project Sin takes an interesting approach to deploy an Argo CD system in every cluster. You can actually have an Argo CD that manages several clusters. That's also possible. So I've chosen to have an Argo CD in every Kubernetes cluster they manage. And then they use the Capitan project, capitan.dev, which is a tool that is meant to generate JSON based on JSONnet. So they're using JSONnet code to generate the code that is passed to Argo CD. And their approach, their take, is that instead of using Helm to deploy dynamically into Kubernetes with Argo CD, they want to use basic YAML files or basic JSON files that are already interpreted, that are already base resources in Kubernetes, and pass them to Argo CD. But they want these files to be generated from code. So they're using Capitan in a tool that they call Commodore that will interpret JSONnet code and generate all the Kubernetes manifest that Argo CD will then apply. And so they store all this resulting manifest into a Git repository that is then passed to every Argo CD cluster. So that's an interesting project to keep an eye on, and they're trying hard to solve the way to manage several clusters with a single repository. So here are a few links to some dev posts I used in this talk, and some of the projects, including the Kubernetes demo, the KUDO demo based on Argo CD that I showed earlier. There, if you have any questions, don't hesitate. Thank you for your attention. And we're also still hiring in Switzerland.
Thank you very much, Raphael, for your talk. So far, I'm looking at the chat in the on YouTube, so no questions unless they come from the 25 last seconds of your presentation. Thank you very much. I would like to share with you as well the last things. So thank you everyone for joining. Wanted to let you know as well if you have a couple of last questions that we didn't have for the past hour and a half, and you're thinking afterward, oh my gosh, I need to get in contact with Jan, Ken, or Raphael for the questions. Please don't hesitate. You can post it on the Meetup site, and we will forward them. And like I mentioned, please, if you need the presentations, you can let us know and your email address, and we'll gladly share it with you. The next event will be for the Cloud Native Romandie. Will still be virtual, that allow us to bring greater speakers from all around the world, like Jan from Berlin or Ken from Chicago. And so will be held on Thursday, November 26th. Afterward, I come back to the Swiss Cloud Native Alliance to let you know that what we are doing. We sometimes share topics, we sometimes share speakers. We are completing one another, and everyone in their own geographical zone from Switzerland. And then I wanted to share with you, I was about to forget, that Tuesday we do the Container and Cloud Native Roadshow, which is entirely virtual from 9 a.m. to 4:30 p.m. You can connect on the link below. So if you're interested, please write to us, and I'll gladly share the invitation with you and the link to connect to this Cloud Native Roadshow. So there will be two different topics. One talk track for the dev specifically, and another talk for the talk session for the operators. And so that would be good. And the last question regarding Slido as well, that what did you prefer about today's meetup, if that's the topic, if that's the speaker, the fact virtual against the fact of being on site like we used to do in Geneva and Lausanne, and as well the schedule, if that's a good schedule for you from Switzerland, knowing if from 5 to 7, if that's a good time, or you prefer a little bit earlier or a little bit later. Please don't hesitate to let us know, and like this, that would be good. Thank you so much. And on this, I will stop sharing my, continue to share the Slido deck, but stop talking. And thank you everyone again for your time, and thank you for joining. And thanks again mainly to Jan and Ken and Raphael for sharing with us their wisdom. Thank you guys.
Thanks, Thierry. Thanks, Raphael. Thanks,
Thank
Ken.
you.